I went through fermions and the spin connection. It could have been done simpler without forgetting about fermions, or just not doing it that way. But nevertheless, they exist. You need to know that information. And it looks much like usual gauge theory, so it's a nice thing to do. We started to see the Feynman rules. I gave you some of them by doing weak field expansion. Gives you the propagators, simple vertices. Today we do this a little more seriously. There's two things. One is first the background field method. And then the second is Fedeev, DeWitt, Feynman, DeWitt, Fedeev, Popov, Ghosts, gauge fixing technique, where we complete the Feynman rules by getting out the Ghosts Feynman rule. I'm going to be doing path integrals, so my start place here is talking about path integrals and a few things there. This is one of the places where, not knowing the background of everybody out there who's listening, I don't know exactly how to pitch it. So apologies if it's too high, too low, whatever. So I provided on the webpage a section out of a more introductory book. This is another book by myself and Lorenzo Sorbo, which is an introduction to path integrals. And then you have the dynamics of the standard model, since you all downloaded it for free. And so there's a path integral, two path integral appendices there. And finally, also on the webpage is something on the background field method, which is an old reference by Larry Abbott, but is sort of one of the places you can see that. Okay, so path integrals. I'm going to use path integral techniques because they work the best here. The alternative would be canonical quantization, where you use phi x with pi of x prime, commutate from commutators, take equal time, and that's IH bar delta 3 of x minus x prime. And that's how we first see quantum field theory. But it doesn't work very well with gauge theories. So it's not too useful. I mean, sometimes people do it. For gauge theories or gravity, basically any theory with constraints. And also, you can also see that especially for general relativity, it's tough because you have equal time commutators, and what is time in general relativity. So instead, it's a very different looking framework, but we define the theory by integrals over the fields, all values of the field at each point in space-time, and the e to the I times the action, and you get the classical theory from the minimum, and the quantum theory from the full path integral, from integrating over those fields. And very different approach, but much more suitable for things like gravity. So since I don't know everyone's background, I'm going to show you the three results that I do use. At various stages, we're going to do the simplest path integral. The simplest path integral is the Gaussian, which is, if I take z of j, and I just take the kinetic energy pieces in there. So this is z0 for the 0th order. That's the integral d phi e to the I. So for I'll do it for a scalar field here, but it's you can generalize it. 1/2 d mu phi minus m squared phi squared minus j phi. It's an easy path integral to do, and it takes some of the mystery out of path integrals because it's just a function. It ends up being some number just called z0 of 0, and then the other piece is e to the minus I integral d4x d4y j at x df of x minus y j of y. And so this is just a simple function with a propagator in there, and this ends up with some manipulations giving you perturbation theory. Okay, and we'll do that at some stages where we'll use that. That's not actually doesn't come much today, but nevertheless there. The other two that we use is doing the path integral over bosons. So here's the boson path integral. It's a formal expression, e to the I integral d4x phi, some differential operator phi. Okay, so there's some operator there. This, with some work, can be some number times the determinant of O to the minus 1/2 power. And we then use some identities about determinants and write this as e to the I minus I over 2 trace log O. Okay. Now this is truly scary, taking the determinant of some differential operator, but we'll see. Actually, this one we will go see today, how it actually connects up to ordinary perturbation theory. And so at the least we'll take some of the mystery out of that. And the third one we also need today is if I do fermions, let's see, fermions is over here, yes. Integral d psi bar, fermions e to the I integral d4x psi bar psi, so it's again some differential operator is n times the determinant of O to the first power. So one has, it goes to the minus 1/2, or if you have two fields, it's -1, complex field is -1. Fermions, it's the positive power. This is going to get used today in our ghost story. And the first one here is going to be used today to the background field story. Okay. So again, I will use them. Hopefully you'll see their use a bit more. Find something interesting in how I'm using them. Okay, so there's the preliminaries. So the first thing I'm going to do is background field, then ghosts. Okay, anyone have anything what you want to say at this stage? Any comments? No comments. I don't see any comments.
Yeah, good, thank you.
Yeah.
Okay.
But so, George, just a second. Can you
Yes.
also look at the Q&A section now? Because you say that you see no questions. So can you actually see them? Also, I mean,
I wouldn't see the questions, but I might see that one exists. And
Okay.
because I see a little thing up on the top of my screen that says Q&A.
All right. All right.
Okay. And
Okay.
so presumably there's something there.
Yeah. So
Last time when I opened that, I actually had trouble getting rid of it. So I might ask someone else to read it if we're not at the end of the lecture.
okay.
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 So if I'm in the middle of things like right now, I would rather have you read it to me.
Yeah, sure. Just today.
But
Okay, but so for the moment, no questions. So
for
you
the
can move
moment,
on.
I don't see anything up there.
Yeah.
Okay. So background field method. So when you're first learning quantum field theory, basically one calculates matrix elements. And so that's S matrices, and that's fine. And you can, many times you can look at those and see the structure of them. They must apply something that looks like a Lagrangian also. And we do that when we do renormalization. So for example, we calculate some diagrams. You look at those diagrams, you say, that looks just like the renormalization of the initial diagram that we operator that we started with. So therefore we renormalize. Background field method is a way of doing some of these in a slightly different pathway, where you do the quantum fluctuations around some background field, and then your answer is going to have that background field there, and so you will actually have an action or a Lagrangian as your answer rather than a matrix element. And so basically you're going to be expanding keeping some background field, some field as a field. Sorry. Okay, and I'm just going to do one as an example, and then we'll do gravity. We'll show you how it works for gravity. But my example is going to be one where you can make some contact with the renormalization techniques that we normally do, because I'll then use that later on when we renormalize gravity. And it also gives some contact into perturbation theory that you know and love. So the example is I'm going to do QED with a massive scalar. So the Lagrangian here is d mu phi star d mu phi. So this is a complex scalar because that's how you describe charged particles in QED. And the Lagrangian is going to be a quarter f mu nu. F mu nu. That's the original Lagrangian for the fermions, for the photons. And this is, we're going to keep in here, we have d mu plus I e a mu, and we're going to keep a mu as the background field. Okay, so we're going to do a loop of the scalar in the presence of this background field. Okay, we'll do this in the path integral formulation, and so let's just transform this a little bit. Basically, the Lagrangian for the scalar, if I integrate by parts, can be rewritten as minus the integral phi star d mu phi. So I basically integrate and collect terms, and it's covariant derivatives once again. And this is my differential operator. So in that path integral formula that I gave, here's my differential operator. And so in particular, and we're going to do perturbation theory. So d mu is usual box. Then there's terms with this background field in it. There's 2i e a mu d mu, where this now acts on phi. There's a piece where the derivative, you can see derivative acts on a plus I e d mu a mu. And then there's a piece that's second order because I have two derivatives and each have an a in it. There's a minus e squared a mu a mu. Okay. And so for the moment, I'm just going to call this thing box plus v of x. And that's the perturbation. And then in a path integral treatment, I have the integral d psi, d phi star. It's complex scalar field, so you have these two. E to the minus I integral d4 x phi o phi star o phi. And that's then the determinant of O. It's O to the minus 1, which is then e to the minus trace log O. And we have to make sense out of that guy. The first step in making sense is that the trace here is, in this case, since they're scalars, is really just means you integrate over all space. It's a diagonal element over all space. So this is e to the minus d4 x log O x. Okay. Actually, I guess let me keep the remaining traits in here. Trace over whatever indices are left. Actually, it's not that necessary here, but you might want to do it meaning sum over the Lorentz indices of the A field. Okay, so that seems scary enough, but it's really not that bad. This is, we have here log of O is equal to log of box plus V. Okay. And the expansion that we're going to do to make sense of this is write this as log box 1 plus 1 over box V. Okay. Just bear with me for a minute and we'll start making sense in a minute. Log box. And since this is a perturbation now, I can expand. So this is then log box plus log 1 plus 1 over box V. And That's log box plus 1. No, the one log of 1 is 0, so it's 1 over box v plus 1 minus 1/2, 1 over box v, 1 over box v plus dot dot dot. Okay. Looking plenty formal, but we're about to turn these into Feynman diagrams. The key to doing so I'm going to then take the x to x matrix element of this. The key to doing this is noting that 1 over box is the propagator. So if I have something that x 1 over box y, so if I have 2 different points there, that's equal times to I times the Feynman propagator. At least that's how we will interpret it here. To make it the Feynman propagator, you need to add a little I epsilon, but let's not worry about I epsilons here. Then if I look at the terms that I have here, these are going to look like Feynman diagrams because I've got interactions and propagators between them. First order is x 1 over box v x integrated over okay, but we here v is a function of x, so we know v of x, it's just the background field, and you then end up with x to x of the propagator, so a propagator from x to 0. So this turns into the integral d for x df x minus x times v of x. Okay. Now, v of x has terms in it that the piece I'm going to look at right out at the moment is the a times a piece. So this contains in it something that has 2 photon fields and a propagator from x to x. Okay, so this is in fact the tadpole diagram. That's the name of this. But in the case that I'm doing, this thing actually vanishes. And it vanishes in dimensional regularization. The IDF of x minus x is the integral d4 k over 2 pi. That's actually dd. 1 over k squared. And that goes to 0 in dimensional regularization. Okay. That's of course one of these funny things that you always love explaining when you're teaching quantum field theory, because it looks like it's quadratically divergent, but in dimensional regularization you can continue to some dimension where this is well defined. There's no factors around, so in that if it's well defined, it has to be 0 because there's no dimensional factors left. Anyhow, I'm going to take that here. So this one doesn't contribute to anything. Second order, we do get something. At second order, we have x 1 over box v 1 over box V X, which if I put a complete set of states in there is X 1 over box V Y 1 over box V X, which, given the correspondence that I had, tells me that we get for this 1/2 the integral d4x d4y. Actually, I need a d4y here. d4x d4y of v of x propagator x minus y, v of y propagator y minus x. Okay, at this stage I've got it, it's now functions, and so I can play with functions. And there's a little work to be done. But what you see that this is coming at is there's an interaction here that involves the gauge field. So in V, there's something linear in A. Then you propagate from X to Y. There's another interaction. You propagate back from Y to X. This is going to be the vacuum polarization. But I've got it as a function of this background field. Okay, at this stage, there's some calculational games. In V, there's various derivatives. I'm going to play, there's in the A field, so there's in here, we've got things with A's and derivatives. I'm going to take derivatives and sometimes integrate them by parts, such that all derivatives act on the D's. So if I do that, I can get things that look like A of X, derivatives on D's, A mu of X, A of Y, nu of Y, some things, mu nu, some matrix here, mu nu. That's a function of propagators and derivatives of propagators. Then there's some various tricks. I'm going to evaluate those propagators using dimensional regularization. And let's see, what do I'm trying to say? So the tricks are things like the following. It's if I have a Feynman propagator, d mu d nu, Feynman propagator, this ends up being some function of, it's actually d times the derivative mu derivative nu minus g mu nu box acting on just the scalar propagator squared. So there's various little tricks there. What I'm doing here, if you're familiar with it, this is the Passarino-Veltman reduction, meaning which tells me that I can take all diagrams and reduce them to the scalar bubble diagram or the tadpole in this case. And then I end up with something. e squared over, so integral d4x, d4y, a mu of x, mu nu of x minus y, a nu of y. Okay, and by doing that, the answer turns out to be that this is g mu nu box minus d mu d nu times the Feynman propagator squared and divided by d minus 1. Okay, so there's some little trick there that, but I've turned it basically into the scalar propagator squared, the bubble. And then overall, I then take this thing and integrate it by parts again. And I've got a change in the Lagrangian, which is integral d4x, d4y. I put these derivatives back on here. It turns into f mu nu of x. Feynman propagator squared over d minus 1, x to y, f mu nu of y. Okay, so the nice feature here is that the original thing was gauge invariant, this is gauge invariant. And so you could have almost guessed that it has to have this form, and let's just write this a little bit. And so by working with this background field, I've put this in a simple form. And now what I have to do is this Feynman propagator squared is a function. It's a singular function. It's going to have two terms in it, one of which is going to be a divergence, and the other will be the finite remainder. So how do you evaluate that? Well, the Feynman propagator squared from x to y is the Fourier transform well, actually, let me, for notation's sake, just keep this as a function of x here. E to the I q dot x of the Feynman propagator squared as a function of q. And this is just a calculation that you know and love. That's the Feynman propagator squared as a function of q is the bubble diagram. And this can then be this df squared of q is it's I over 16 pi squared 1 over epsilon. This is, I'm doing dimensional regularization, minus gamma plus log 4 pi minus log q squared over mu squared. This is the massless. I've done this for the massless case, and that's, you get a log q squared. And so this tells me that the Feynman propagator of x squared of x minus y is the Fourier transform of this 1 over epsilon log q squared. And there are then two pieces to that. This is then the Fourier transform of the first piece is a delta function equals I over 16 pi squared 1 over epsilon plus dot 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 of delta 4 of x minus y. And the second piece is some non-local function. I'll just call it. This is the Fourier transform of log. Okay, so what we've found here is the divergences in this diagram. Divergences are local. Which is a lesson in itself. But if we then add this to the original action, so now I get the one loop effect of action. I get S is equal to S of the photon field plus S of the one loop. Let me call it delta S. I end up with integral d4x minus a quarter f mu nu times some constant. It's z3 to the minus 1 is its standard notation, which is the sum of the original way back here, the original photon Lagrangian, and this correction, which also has ff at the same point. I get that, and then I get a finite correction, which is some constant b e squared integral d4 x d4y f mu nu of x minus y x L of x minus y f mu nu of y. Okay, so what I've done here is by doing this loop, I've got, and holding this photon field as a constant, I've renormalized. I found the renormalization constant for F by basically doing the Feynman diagrams, but I've done it with this field in the background, and I have an extra correction here. This correction here, at this stage, I'm not going to do anything with it, but hold this for later. We will actually see those pieces and explain them later. You'll hear me say Barvinsky, Velkovitsky at some stage, BV, Barvinsky, Velkovitsky. When we're doing gravity, these reappear in the gravitational action, but with curvatures there. Okay. Let me actually stop and take some questions at this stage. There was a somewhat sizable calculation there that I went through. Anyone want to ask any questions about that? There is a question just came up.
Yeah, the question, okay, Ahmed was asking what is the d-1 which appeared in calculation and where did it exactly come from?
Okay, so yes, the d-1. D is the number of dimensions and d-1 is then roughly 3. And it came from the following. Here's the basis where you see it. There's in these things where I'm saying I'm using dimensional regularization. There's a bunch of identities. The place you've probably seen this before is if I had, for example, d for k mu k nu over. So I'm basically doing this integral. There's a piece here with g mu nu in it, and there's a piece where q mu nu, and when I'm trying to do this, I will contract these to get a scalar integral. So basically, it's an easy integral to do by contracting this. If I do G mu nu here, G mu nu there. I'm sorry, that was bad notation. Sorry, I'll correct that later. I get a factor of D here. And so there's some coefficients here. And so when I'm solving for the various pieces, I get factors of D. So it basically was that identity right there. That piece right there. Ended up going to D minus 1. So in the background here, going from this expression up here to this one down here, there are factors of D involved. Is that sufficient explanation to trust what I did? It's this calculation actually exists in the literature. Why don't I put it on the page, the web page? I'll put the calculation on the web page, where we do all the steps in great detail. Okay.
Yeah.
Okay.
Okay, then there's another question. Okay, Ahmed said thanks, so I guess
Okay.
it's okay as an explanation for the moment. And there's another question by Ashwin. Say, we could only get tadpoles and bubbles here. So is it safe to assume that box and triangle contributions related only spin to particles? So are related only. Okay.
No, so if I could get more than that too. I just have stopped in this expansion here. The next order term here would have been triangles and boxes. And so eventually in this construction, I would have had the full perturbative expansion. I would have had the tadpoles, the bubbles, the triangles actually in the case of QED vanish, but I do get boxes. I get 4. I get and so this is the order E squared. This is order E to the 4th. I've just done the first leading term, and they're all the terms in the perturbative expansion right there.
Okay.
Okay.
It's fine for Ashwin as well. Seems. Yeah.
Okay. So let me just do one generalization, because this actually also comes back. So this calculation can be done. As I say, I'll post the calculation on the web page. A slight generalization of this is just the following: is if I take phi star d mu, so this is just slight change in notation, covariant derivatives plus some function of x phi, and I let these things be any number of fields that I want, and I write this as d mu plus some gamma mu. It's then a simple thing to do, go through exactly the same steps. We've done the facts of the d mu's. The sigma is even easier, because I basically just get sigma propagator sigma. And so then delta S here is integral d4x, d4y, trace of gamma mu nu. So it's the field strength tensor formed with that. I get this delta F over 4 d minus 1, x minus y, gamma mu squared, gamma nu. And then the other piece is 1/2 sigma of x df squared x minus y, sigma of y. So you can almost do that in your head. The thing that I haven't shown you is if this is multi-component, this gamma mu nu is it's d mu commuted with d nu, which is d mu gamma nu minus d nu gamma mu. It's this field strength tensor. So this is just what it has to be. It's a larger invariant field strength tensor. And then I can pull out the divergences. The divergence is delta S divergent integral d4x 1/16 pi squared 1/epsilon. And the answer is, where up here I had this d 1/4 d minus 1. Actually, I guess I needed a 1/4 there. This becomes 1/12 gamma mu nu gamma mu nu plus 1/2 sigma squared. The 1/12 is the 1/4 times d minus 1 is 3. Sorry. And what I've just sketched the derivation for, it's clear I haven't done all the steps. This is something that we'll see later on. It's called the A2 heat kernel coefficient. And it encompasses the renormalization of this theory plus many other theories. Okay, so what I've pulled out and ask you to hold till later is that this is a particular divergent coefficient that I can calculate in a general background field method, where this is some background field. That's another background field. I can put the action into that form. I know the divergences by having just done this simple calculation. Okay. So at this stage, I'm going to transition to background field, general relativity. And from there to ghosts, and I think I'll be okay on timing. When we're doing general relativity, we also have the situation where instead of having two separate fields, I'm going to expand around some background. So the expansion here is going to be that g mu nu of x is going to be some background field plus a fluctuation. I'm going to call this thing, like I did in the weak field approximation, H. But instead of expanding around flat space, I'm expanding around a general background. I then expand all the quantities. So the connection can be expanded as the connection for the background. Sorry, jump in. Let me put one bar under it. The 2 bars, this in this stage means order H and order H squared. Okay, the curvature will be the curvature of the background plus something of order H, something of order H squared. And these are not that hard to do. They're just algebra. I'm not going to do it for you, but let me just write out. So remember, I'm going to write out the first order one for gamma. Because there's one point I want to make on it. Remember, gamma itself was the connection was 1/2 G lambda sigma d mu G. I'm sorry, this is d sigma. No, it's not. Back up. D mu G sigma nu plus various other terms. Okay. The first order expansion, you can sort of see the first order term is going to have these expands terms that are 8 of order H here. And there's going to be some terms that come from here. These, we have a gauge invariant system, so this is going to organize itself as 1/2 G bar lambda sigma. So everything is now with this background metric. It's going to involve derivatives of H. But the derivatives are going to have they're going to be covariant derivatives with respect to the background field. So the answer is H sigma mu minus D sigma H mu. Okay. And the point of showing this is it's covariant with respect there's then a gauge invariance with respect to the background field. So if I let X prime mu equals X mu plus some little C mu of X. And actually this is D. Actually, so the differential form is dx plus it involves the derivatives acting on this field. And the field H, so we know how G transforms. Actually, no, actually, we don't know how G transforms. I guess I should do that one out. G prime mu nu of X prime is J mu minus 1 J lambda G beta of X prime J nu beta minus 1. This is equal to the G mu nu at X prime minus let's see if I can get this quickly. G alpha nu d mu C alpha minus G beta mu d nu C beta. And I expand this guy as G mu nu of X plus C alpha d mu G mu nu of X. Sorry, I've got too much algebra going on here, but let's write it. The answer is G prime mu nu is G mu nu minus G alpha nu C mu d, d mu C alpha minus G alpha u d nu C alpha plus C alpha G mu nu. Okay. My goal in this, so this is actually the standard weak background field gauge invariance for G in itself. If I then do the background, the expansion, the H prime mu nu is H mu nu plus covariant derivative on C nu plus covariant derivative C nu. This was just the background field generalization of the flat space result. And perhaps I could have just jumped straight to that. There's a gauge invariance that basically shifts H by the derivatives of this gauge transformation parameter, but they're covariant derivatives. Okay. So, bunch of algebra. At this stage, I'm just going to give you the result. I'm going to copy the result and sorry. paste it in here. Not that anyone cares too much detail, but there's what the answer is when you get to the end. The points that are relevant for us now is that this is gauge invariant. And it's a function of the background field curvatures and covariant derivatives. This will end up going into our overall Lagrangian. This is just the generalization to curve space of the one that I did in flat space before. Okay. Okay. So this is, if I'm following the same procedure I did with flat space, but now in this background field method, I need to do gauge fixing. So previously I chose the harmonic gauge condition d mu h mu nu minus d nu h lambda lambda equals 0. And the gauge fixing Lagrangian was 1/2 this thing squared. Okay. The generalization here I'm just going to do is just convert these. There's some constraints. C nu equals the covariant derivative on this background field. And the gauge fixing Lagrangian would be the square of that. Okay, so gauge fixing is going to proceed, but with just covariant derivatives. At this stage, I have to go into, I'm transitioning to ghosts. So I'm first going to tell you some ghost stories. And then we'll do the construction and then we'll be finished. Okay, so the ghost stories, I'm going to go back to that paper by Feynman. So I posted the Feynman paper, and in it he does two remarkable things. The first is he made a discovery which is the called Feynman's tree theorem. Copy this and put it in the other file. Feynman's tree theorem is the relationship between closed loop diagrams and diagrams without closed loops. So these are the trees. And by unitarity, you can connect these two diagrams. So, and this is the basis of a modern technique, which is unitarity-based quantum field theory, where you use tree level diagrams to construct loop diagrams, and you can express any diagram with loop circuits in terms of diagrams with trees. And that's great because we know how to do tree diagrams, and it's easy to do tree diagrams. So that's statement number one. Then Feynman starts doing the calculations using these diagrams. Got this guy. And he notices a problem. I'll explain that in a second. In general relativity and Yang-Mills. So he notices that he has a little disease. The calculations in general relativity don't seem to work this way. So even though he has this theorem, it doesn't seem to work. He has a disease, and gravity isn't alone. Yang-Mills has it also. Okay, so what does he do? So he assumes the tree theorem to be true, and uses it in reverse. And he then knows how to calculate in GR. So he knows how to do graviton loops and closed loops and etc. It gives a different answer than he finds using the standard ways, and his solution is ghosts. Here's the solution. Let's see. Put it in. His solution is that to make it gauge invariant, you subtract from the answer loops, rings as loops, that also add a little different particle going around, an artificial dopey particle, which is now what we call ghosts. It's a vector particle. In the case of gravity, we'll see it's a scalar for QED, but it's a vector in gravity. And it's also fermionic, where the fermionic part comes from the fact that you have to subtract it. Okay, so there's where ghosts enter into physics. First, you see then in the article, you see DeWitt asking about this tricky little particle, and Feynman says, "Give me 10 more minutes, and I'll show you I can do math that nobody can understand." Now, basically, the history here is that then DeWitt formalizes this. Somewhat simultaneously, Fadeev and Popov did it for gauge theories. Etc. Okay, but Feynman's insight there is the original one, and so the formalism is a bit funny. If you've not seen this, we'll see if we can point out the key part of that. But the logic is the following. the logic is that if I just impose the gauge symmetry on the Lagrangian, I've changed the Lagrangian. So what I have to do instead is I have to make sure that I don't change the Lagrangian. And the way to do that is to insert unity. Into the path integral. In a clever way, of course. We're going to do that by something which is the generalization of unity is the integral over some variables. Delta of, I'm calling it f of x, some function times the determinant of the function, sorry, equals 1. So if I just had delta of x, then the integral of dx of x is 1. But if I have, I'm sorry, excuse me. I've got many variables. In the change of variables, I get a determinant. So I'm going to stick this into the path integral. The early stuff here is going to turn into gauge fixing. And the determinant I'm going to evaluate using the determinant of some operator is the path integral over fermions. So that path integral relation is how you do that. This is the interesting part. This is the Gauss. The determinant of this in this identity is the Gauss fields. Okay. The field theory steps are the following. And given the time, I'm going to just focus on just the fermion part. The gauge invariants. Let's do gauge theories first. So like QED, the gauge transformation is some linear transformation. The constraint is equals 0, or I could equally well make it to be a constant. Okay. So the factor of unity that one inserts is going to be the integral d theta, these overall possible changes, delta f of a of theta minus some constant times the determinant okay. Given the time, let me focus only on the determinant part. This part turns with some manipulated turns into the gauge fixing. And I guess perhaps I should promise to write that out for you. steps out for that before I post the notes. The part that is new, so if you just did this, you'd have an awkward way of arriving at gauge fixing. Basically, you've put a delta function constraint in the action. And it's equivalent to adding the gauge fixing term in the Lagrangian. I'm going to leave a page there for a little written discussion of that. The interesting part, though, is the determinant. We have the determinant of the f, the theta, and in a gauge theory, we write this as the path integral over fermion fields, dc, dc bar. These are the ghost fields. E to the I integral d4x c bar df d theta c. And so this is then a new term in the action. Which is the ghost term. To calculate that, let's go back and do it for QED. In QED, the constraint was that d mu a mu equaled some constant. Okay, so what sat there was the delta function of f of x. And f was the derivative minus some constant. The variation then of f with respect to theta is, well, d mu a mu. If I vary with respect to theta, I get d mu theta. Actually, sorry. F prime is this with a d mu theta. So if I do a gauge transformation, so the df d theta is derivative on theta box theta. Well, is box. In the case of QED, the ghost action is C bar box C for QD. If I do the same thing for QCD, or Yang-Mills, the ghost Lagrangian is almost that as C bar box Fij d mu a mu k ck. There's a non-trivial piece in the Yang-Mills case. And the effect of this is to remove, then just like Feynman said, remove unphysical degrees of freedom in loops. When I do loops of Yang-Mills plus loops of these ghost fields, I get the gauge invariant vacuum polarization. So Feynman did this by taking these diagrams and converting them using his tree theorem. The DeWitt Fedaya-Popov reformulation of this uses this fancy formal construction, but gets the same answer that you do the graviton calculation or the gluon calculation and you subtract off the ghosts. All right. One more step and we're almost there. I now want to do this for gravity. Okay, I'm just following the same old steps. The constraint here was that I'm going to impose is d bar mu h mu nu minus 1/2 d bar nu h lambda lambda and the constraint that I'm going to add in is I'm going to add in a delta function of c nu minus some constant. This ends up with a procedure that I have not explained. It gives me the gauge fiction Lagrangian of 1/2 c nu, which is what we expected, is just that Lagrangian squared. And so that is a piece we could have just added by hand, but the piece that is new is the ghosts. We need to calculate the determinant of the constraints with respect to the gauge parameters. Okay, so let's do that. It's what I. All right, you have to bear with me just a couple minutes to finish this piece. I need to finish this. Remember, h mu nu went to h mu nu plus covariant derivative and so then delta c mu nu is something that's calculable. Is I've got c as derivatives on h, so it's d bar mu d nu c mu plus d bar nu minus 2 over 2 d nu d mu c mu. Okay, so basically I'm just plugging that into the original constraint. This is equal to d bar nu c nu, plus if I've minus, if I've got my indices correct while I'm copying here, is d bar nu d mu c mu. This turns into curvatures. And so this is then g mu nu d bar squared plus r bar mu nu c nu. And so this is the equivalent of what we had before in QED. This was just f squared. In QCD, it was the term box plus something. Here's what it is for the gravity case. And then this gives us our answer. Because there's two indices here, we have to have a vector indices on it. The ghosts, let's call them eta mu, and the ghost Lagrangian is g bar. No, I'm sorry. Eta bar mu g mu nu d squared plus r mu nu eta nu. It's basically this factor. Gives us the ghost Lagrangian. And we end up with a new rule. A graviton hooking up to this. And let me actually fill that in later also. It's just some functions. It's like two derivatives. So two factors of momentum. But then I wanted then at this stage end up with a summary of where this logic has taken us. The logic has taken us that I've defined the theory by the path integral over the graviton fields, and the ghost fields. And I have in the exponential e to the I d for x square root of minus g bar. I have the background field. I have the gauge fixing piece, which is a function of h, and I have the ghost fields piece, which is a function of eta bar and g. Okay, so I've got my full quantum action. I've got now all my Feynman rules, and I can add matter to this. So that's basically the development that I needed to get done today. When we come back in August, we're going to start treating this, doing loop diagrams of matter fields, doing loop diagrams of gravity fields, pulling out predictions, and trying to apply this. But I've now fully defined my gravitational theory. All right, so I need to stop just because I've run out of time, and I see there will be questions. So let's take questions at this stage and then wrap up for today.
All right.
So since lecture over, do you like to read the questions directly, or do you
I
still
think
want
I
me
can
to
do
read
that.
it?
Yes, let's just see. Ah,
All right.
okay. So the question is, are ghost loops considered during renormalization process, even though they are unphysical? And the answer is yes. And we can turn to QCD for this as an example. When we're renormalizing gauge theories, some of the important diagrams come from vacuum polarizations, where you put the matter fields in, you put the gravity fields in, and you put in the ghosts. This is Yang-Mills. This is matter. And then there are some other vertices that we have to add also, but let's just talk about. You have to add diagrams like that also for Yang-Mills, but yes, they enter only in closed loops. And they always enter only when the gluon fields enter diagrams. They're part of the same calculation. So you do the gluon field and the gauge that you want, you add the ghost fields that are appropriate for that gauge. And then that gives you the renormalization constants. The same thing will happen in gravity. So this is when we renormalize gravity later on, we're going to have to add the graviton loops plus the ghost loops. I hope that answers the first question.
All right. Okay.
So the Gribov problem. So there's not much discussion that I know about the Gribov issue in gravity, but there's some, and yes. So the answer is we shouldn't. I'm not going to be able to summarize that here at the moment, but the answer is that the gravity case is very much parallel to the Yang-Mills case.
Okay. Yeah, then, okay, another question. Johnny.
Yeah. So can we create a non-classical background gravitational state by Wick rotating, and is there some constraint caused by matter fields living on it? So certainly in flat space, we know the Wick rotation is a way that we calculate the answers. Basically, it's in some sense just a tool. In gravity, the Wick rotation is a more debatable technique because it changes the topology of your states. So the Wick rotation of something that in Lorentzian signatures is an open manifold becomes a closed manifold. It's certainly a whole separate research area where one does that. And so the answer is it's a respectable but controversial technique in the gravitational theory when you're in non-trivial backgrounds. For us, since I'm fortunate only to have to teach perturbative quantum gravity, I'm going to be able to do Wick rotations because I'm doing perturbation theory near flat space. So I'm going to try to avoid answering that question in general.
All right. Okay. Probably the last two questions.
Yeah.
So, yeah.
is there any interest in KMS conditions in extract temperature? I'm not sure. Extract temperature, is that a typo? So the issue is if the question is, do we do finite temperature field theory? You can do finite temperature field theory with some issues. If you're doing some non-trivial backgrounds like de Sitter or Schwarzschild, of course, there's this very famous fact that Schwarzschild radiates, so there's temperatures associated with those. So I'm not sure if the question was meaning either of those conditions, either of those properties.
Okay. Good. Then, okay, just the last one. Okay, but it's just asking for suggestion of some theoretical references.
So the references related to the ghosts and background fields, I think to see more details along the lines that I presented here, my favorite reference is my EPFL. But to be what I should have said early on is that the background field method and this ghost Lagrangian is, I'm not a historian, but to my knowledge, the first appearance of that in the literature was a paper by Tufte and Veltman, which is going to go up on the web page. Maybe I'll stick it up now. It was planned to be later because they also in that paper do loops of gravitons, but the paper is obviously correct. However, I find it a little hard to penetrate, but nevertheless, there it is. It's a great reference. Everyone should read it. It'll be on the webpage soon too.
All right. So, okay, there are no raised hands. So I guess that we can say that the first half of this course is,
Okay.
oh, wait. Oh, okay. If you want just last second question. So asking for Hamiltonian formulation.
No, let's not write. The question is, can we write the Hamiltonian instead of the Lagrangian? We're using path integral methods because we really want to work with the Lagrangian. There is a Hamiltonian construction, but it's hard to turn it into a practical calculational tool for, and that's partially because of the fact that Hamiltonians are not invariants under the symmetries. They're not invariants under Lorentz invariants even. The Lagrangians are invariant, and so in order to deal with all the invariances of the theory, we choose a Lagrangian formulation rather than Hamiltonian.
Okay.
So there's another question about, are we going to do the generalized unitarity? I do have planned to do some of that. It's the topic can be very large, but there's a nice example that I can show you that illustrates how one can do both a double copy and which is the equivalence between gravity and a gauge theory, and how one can use unitarity to reconstruct amplitudes. So yes, I do have that planned in the subsequent lectures.
All right. Okay. So thank you from Ash and Ivan, but also thank you from us for this lecture.
Well,
And yeah, I think that okay, we have to organize, say, the other part of the course. So I mean, since it will be in August, I mean, we have time to organize that privately. So I mean, John, when you feel you're ready, when you have some precise dates, you can tell me, and we'll try to fix the other part.
some dates.
Yeah.
Okay. Very
Okay.
good. Well,
So
thank you very much.
thank
We'll
you
see
again.
See you in a bit.
Thank you, John.
All right.
Yes. Bye-bye.
Okay.